In this segment, we will talk about SPC charts or control charts and how they measure process change. So to detect a change in a process, we need a tool, and that's going to be the SPC chart. And these charts answer these questions. Has the process center, or the average, changed in a meaningful way? And that's going to be what we refer to as the X bar chart. Second, has the process variation changed in a meaningful way? That would be what is measured on what we call the R chart, or the range chart. The SPC charts are also called Short charts, or X bar and R charts. And a control chart is the meaningful way for detecting noteworthy changes in the process average and process variability, as I mentioned previously. Please note that the range is simply the maximum value for that measurement period, like the 5 samples. Take the largest number, subtract the smallest number, and that gives you the range, such as 5 minus 2, the range would be 3. More importantly, X-bar and R charts serve as a guide for deciding when and how to take corrective action to return the process to stability or predictability, or in more common terms, bring it back into control. Here's an example of an X bar chart. I'll show you the R chart in detail in just a minute. And there are some lines on this chart. One is the lower control limit for the X bar, which is X bar is just a fancy way of saying the average. And notice it does not say lower specification limit. It does not take into account what the engineering people say the specification needs to be. It is simply what the process is currently capable of operating to. So lower control limit, not lower specification limit. Up here is the upper control limit for the X bar. Here is the X bar line, which is really right here, and that simply is the average of the averages. And finally, these are the individual X bar or average recordings over each 2 hours, as you can see here. It's not always 2 hours. It could be 1 hour, it could be 30 minutes, it could be 4 hours. You have to decide that based on the sensitivity of your equipment and the process. Here is the R chart, very similar to the X bar chart, except for we're looking at ranges instead of averages. So here's the upper control, not specification, limits for the R, the range chart, the lower control limits, and here is the R bar, or the average of the ranges for the period of time that we're looking at. These individual values are just the range values in here. I do want to point out a few things. The control limits, like I said earlier, are not to be confused with the specification limits, which are determined by design engineers and are based on how the process is currently performing. Control limits are based, again, on how the process is currently performing, not what the engineering people say that it needs to perform to. It is possible and often likely that the equipment is operating predictably. It operates in a fashion that says it's behaving like it should, staying between the upper and lower control limits, yet not producing parts that meet engineering specification limits. When that happens, there's typically a coming together and deciding, is the specification too tight that the engineers said, or do we need to invest in some different equipment perhaps that brings our control limits in tighter by having maybe a more sophisticated piece of equipment. In general, as long as recorded points stay between the upper and lower control limits on each chart, between this limit and this limit, as well as between this limit and this limit, the process is considered in control or operating in a predictable manner, but we always use the term in control or out of control. So how can a process be in control but still making defective products? That simply is a situation where the machine is operating in a predictable manner, is just not operating well enough to meet the design engineering specifications. Next, how can a process be considered out of control but making 100% acceptable products? To illustrate this, let's pretend that you are driving on a 4-lane highway, 2 lanes going in one direction, 2 lanes going the other direction. Technically, you are operating in specifications if you stay on the road. However, you could be swerving erratically even within your own lane and still be operating to the specifications of not going off the road. It could be in real life that the process is operating very erratically, jumping all over the place, but the specifications are so wide that it never really exceeds the engineering specifications. Let's take a few moments to look at examples of out of control processes. Now, you typically look at the X bar average charts and the R chart variability charts together, but for this illustration I'm going to break them apart. So here is an X bar chart, and as you can see, here's the average of the averages. Here are your averages recorded over every 2 hours, and here are your upper control limits and your lower control limits. So things are going along okay, then all of a sudden you exceed your lower control limit here. Something has caused your process to go out of control. So you do something about it, hopefully, and you make an adjustment, whatever, and the next reading is okay, okay, okay. In summary, the process goes out of control at 2 p.m. because it exceeds the lower control limit, not the specification limit. The specification limits do not typically go on charts, and definitely not on X bar and R charts. At this point in time, we should investigate right here the problem as to why our process average has shifted, because we're looking at the X bar chart. Determine the root cause of the problem, what is causing this, and take corrective action to bring the process back into control, operating in a predictable manner without any specific assignable causes. When it operates between the upper control limits and lower control limits, it is considered to be in control, operating predictably. For the upcoming exam, we typically look at the whole run and comment about when it went out of control and when it did not go out of control. But in reality, we should be investigating the root cause at 2 p.m. rather than allow the process to continue running in an out of control manner. For our purpose, we assume that the problem was actually investigated, root cause determined, and corrective action taken at 2 p.m. If corrective action had not been taken at 2 p.m., it would be highly unlikely that the process would have corrected itself, as is shown by the 4 p.m. to 10 p.m. readings. So, to recap, what is the difference between a control limit and an engineering specification limit? With one specific exception, the specification limit should not be on a control chart, and we will not go into the specific exception in this course. An example, let's say our specification was 24 to 26 inches. 4 sample measurements taken at 3 p.m. were 10, 30, 20, and 40. Based on these 4 examples, X bar was 25. So the X bar, the average of these 4 readings, is within specifications. But this is out, this is out, this is out, this is out. So taking an average and applying it to a specification makes no sense, because it all revolves around each individual measurement must be within specifications. So this is why you do not put specification limits on control charts. Let's delve into the R chart, which accompanies the X bar chart whenever we're showing the graphs. The range varies like this over time. All of a sudden it spikes here, and hopefully we've done something about it, and it drops down and it seems to be doing okay, then it spikes again. So if I was interpreting this, the process goes out of control at the 5th and 8th time periods because it exceeds the upper control limit, which is right here, not the specification limit. At these points in time, we should immediately investigate the problem as to why our process variation has increased. Not our process average, that's what the X bar chart does. This has to do with the tails have gotten larger in this case. Determine the root cause of the problem and take corrective action to bring the process back into control, operating in a predictable manner without any specific assignable causes. Again, like I mentioned in the X-bar chart, in reality we should be investigating the root cause at the 5th time period rather than allow the process to continue running in an out of control, non-predictable manner. Likewise, we should be investigating the root cause at the 8th time period rather than letting the process continue running in an out of control manner. For our purposes, we assume that the problem was actually investigated, root cause determined, and corrective action taken at the 5th time period. The process then appears to operate in control for the 6th and 7th time period, right here, before going out of control again at the 8th time period, where the problem was again promptly investigated, root cause determined, and corrective action taken. If corrective action is not promptly taken when the out of control situation occurs, it would be highly unlikely that the process would correct itself.